Penrose tiling is a non-periodic tiling generated by an aperiodic set of prototiles. Penrose tilings are named after mathematician and physicist Roger Penrose, who investigated these sets in the 1970s. The aperiodicity of the Penrose prototiles implies that a shifted copy of a Penrose tiling will never match the original. A Penrose tiling may be constructed so as to exhibit both reflection symmetry and fivefold rotational symmetry, as in the diagram at the right. A Penrose tiling has many remarkable properties, most notably, it is non-periodic, which means that it lacks any translational symmetry. It is self-similar, so the same patterns occur at larger and larger scales. Thus, the tiling can be obtained through inflation, and any finite patch from the tiling occurs infinitely many times. It is a quasi-crystal. Implemented as a physical structure, a Penrose tiling will produce Bragg diffraction, and its diffractogram reveals both the fivefold symmetry and the underlying long-range order. Various methods to construct Penrose tilings have been discovered, including matching rules, substitutions or subdivision rules, cut and project schemes and coverings. Background and history. Periodic and aperiodic tilings equals. Penrose tilings are simple examples of aperiodic tilings of the plane. A tiling is a covering of the plane by tiles with no overlaps or gaps. The tiles normally have a finite number of shapes, called prototiles, and a set of prototiles is said to admit a tiling or tile the plane if there is a tiling of the plane using only tiles congruent to these prototiles. The most familiar tilings are periodic. A perfect copy of the tiling can be obtained by translating all of the tiles by a fixed distance in a given direction. Such a translation is called a period of the tiling. More informally, this means that a finite region of the tiling repeats itself in periodic intervals. If a tiling has no periods, it is said to be non-periodic. A set of prototiles is said to be aperiodic if it tiles the plane, but every such tiling is non-periodic. Tilings by aperiodic sets of prototiles are called aperiodic tilings. Earliest aperiodic tilings equals. The subject of aperiodic tilings received new interest in the 1960s when logician Hao Wang noted connections between decision problems and tilings. In particular, he introduced tilings by square plates with colored edges, now known as Wang dominoes or tiles, and posed the domino problem to determine whether a given set of Wang dominoes could tile the plane with matching colors on adjacent domino edges. He observed that if this problem were undecidable, then there would have to exist an aperiodic set of Wang dominoes. At the time, this seemed implausible, so Wang conjectured no such set could exist. Wang's student Robert Berger proved that the domino problem was undecidable in his 1964 thesis, and obtained an aperiodic set of 20,426 Wang dominoes. He also described a reduction to 104 such prototiles. The latter did not appear in his published monograph, but in 1968, Donald Knuth detailed a modification of Berger's set requiring only 92 dominoes. The color matching required in a tiling by Wang dominoes can easily be achieved by modifying the edges of the tiles like jigsaw puzzle pieces so that they can fit together only as prescribed by the edge colorings. Raphael Robinson, in a 1971 paper which simplified Berger's techniques and undecidability proof, used this technique to obtain an aperiodic set of just 6 prototiles. Development of the Penrose tilings equals. The first Penrose tiling is also an aperiodic set of 6 prototiles, introduced by Roger Penrose in a 1974 paper, but is based on pentagons rather than squares. Any attempts to tile the plane with regular pentagons will necessarily leave gaps, but Johannes Kepler showed, in his 1619 work Harmonics Mundi, that these gaps could be filled using pentagrams, decagons and related shapes. Acknowledging inspiration from Kepler, Penrose was able to find matching rules for these shapes, in order to obtain an aperiodic set. His tiling can be viewed as a completion of Kepler's finite or pattern, and other traces of these ideas can be found in Albrecht Darwin-Courtoret's work. Penrose subsequently reduced the number of prototiles to 2, discovering the kite and dart tiling and the rhombus tiling. The rhombus tiling was independently discovered by Robert Ammon in 1976. Penrose and John H. Conway investigated the properties of Penrose tilings, and discovered that a substitution property explained their hierarchical nature. Their findings were publicized by Martin Gardner in his January 1977 Mathematical Games column in Scientific American. In 1981, de Bruage explained a method to construct Penrose tilings from 5 families of parallel lines as well as a cut and project method, in which Penrose tilings are obtained as 2-dimensional projections from a 5-dimensional cubic structure. In this approach, the Penrose tiling is viewed as a set of points, its vertices, while the tiles are geometrical shapes obtained by connecting vertices with edges. The Penrose tilings. The 3 types of Penrose tiling P1 and P3 are described individually below. They have many common features. In each case, the tiles are constructed from shapes related to the pentagon, but the basic tile shapes need to be supplemented by matching rules in order to tile aperiodically. These rules may be described using labeled vertices or edges, or patterns on the tile faces. Alternatively, the edge profile can be modified to obtain an aperiodic set of prototiles. The original pentagonal Penrose tiling Penrose's first tiling uses pentagons and 3 other shapes, a 5-pointed star, a boat, and a diamond. To ensure that all tilings are non-periodic, there are matching rules that specify how tiles may meet each other, and there are 3 different types of matching rule for the pentagonal tiles. It is common to indicate the 3 different types of pentagonal tiles using 3 different colors, as in the figure above right. Kite and dart tiling Penrose's second tiling uses quadrilaterals called the kite and dart, which may be combined to make a rhombus. However, the matching rules prohibit such a combination. Both the kite and dart are composed of 2 triangles, called Robinson triangles, after 1975 notes by Robinson. The kite is a quadrilateral whose 4 interior angles are 72, 72, 72 and 144 degrees. The kite may be bisected along its axis of symmetry to form a pair of acute Robinson triangles. The dart is a non-convex quadrilateral whose 4 interior angles are 36, 72, 36 and 216 degrees. The dart may be bisected along its axis of symmetry to form a pair of obtuse Robinson triangles, which are smaller than the acute triangles. The matching rules can be described in several ways. One approach is to color the vertices and require that adjacent tiles have matching vertices. Another is to use a pattern of circular arcs to constrain the placement of tiles. When 2 tiles share an edge in a tiling, the patterns must match at these edges. These rules often force the placement of certain tiles. For example, the concave vertex of any dart is necessarily filled by 2 kites. The corresponding figure is called an ace by Conway. Although it looks like an enlarged kite, it does not tile in the same way. Similarly, the concave vertex formed when 2 kites meet along a short edge is necessarily filled by 2 darts. In fact, there are only 7 possible ways for the tiles to meet at a vertex. 2 of these figures are namely, the star and the sun have fivefold dihedral symmetry, while the remainder have a single axis of reflection. All of these vertex figures, apart from the ace and the sun, force the placement of additional tiles. Rhombus tiling The third tiling uses a pair of rhombuses with equal sides but different angles. Ordinary rhombus-shaped tiles can be used to tile the plane periodically, so restrictions must be made on how tiles can be assembled. No 2 tiles may form a parallelogram, as this would allow aperiodic tiling, but this constraint is not sufficient to force aperiodicity, as Figure 1 above shows. There are 2 kinds of tile, both of which can be decomposed into Robinson triangles. The thin Rome T has 4 corners with angles of 36, 144, 36 and 144 degrees. The T-Rome may be bisected along its short diagonal to form a pair of acute Robinson triangles. The thick Rome T has angles of 72, 108, 72 and 108 degrees. The T-Rome may be bisected along its long diagonal to form a pair of obtuse Robinson triangles. In contrast to the P2 tiling, These are larger than the acute triangles. The matching rules distinguish sides of the tiles, and entail that tiles may be juxtaposed in certain particular ways but not in others. Two ways to describe these matching rules are shown in the image on the right. In one form, tiles must be assembled such that the curves on the faces match in color and position across an edge. In the other, tiles must be assembled such that the bumps on their edges fit together. There are 54 cyclically ordered combinations of such angles that add up to 360 degrees at a vertex, but the rules of the tiling allow only 7 of these combinations to appear. The various combinations of angles and facial curvature allow construction of arbitrarily complex tiles, such as the Penrose chickens. Features and constructions. The golden ratio and local pentagonal symmetry equals. Several properties and common features of the Penrose tilings involve the golden ratio I =2. This is the ratio of chord lengths to side lengths in a regular pentagon, and satisfies I = 1 + 1/I. Consequently, the ratio of the length of long sides to short sides in the Robinson triangles is I:1. It follows that the ratio of long side lengths to short in both kite and dart tiles is also I:1. As are the length ratios of sides to the short diagonal in the thin Rome T, and of long diagonal to sides in the thick Rome T. In both the P2 and P3 tilings, the ratio of the area of the larger Robinson triangle to the smaller one is I:1, hence so are the ratios of the areas of the kite to the dart, and of the thick Rome to the thin Rome. Any Penrose tiling has local pentagonal symmetry, in the sense that there are points in the tiling surrounded by a symmetric configuration of tiles. Such configurations have fivefold rotational symmetry about the center point, as well as 5 mirror lines of reflection symmetry passing through the point, a dihedral symmetry group. This symmetry will generally preserve only a patch of tiles around the center point, but the patch can be very large. Conway and Penrose proved that whenever the colored curves on the P2 or P3 tilings close in a loop, the region within the loop has pentagonal symmetry, and furthermore, in any tiling, there are at most 2 such curves of each color that do not close up. There can be at most one center point of global fivefold symmetry. If there were more than one, then rotating each about the other would yield 2 closer centers of fivefold symmetry, which leads to a mathematical contradiction. There are only 2 Penrose tilings with global or pentagonal symmetry. For the P2 tiling by kites and darts, the center point is either a sun or star vertex. Inflation and deflation equals. Many of the common features of Penrose tilings follow from a hierarchical pentagonal structure given by substitution rules. This is often referred to as inflation and deflation, or composition and decomposition, of tilings or tiles. The substitution rules decompose each tile into smaller tiles of the same shape as those used in the tiling. This shows that the Penrose tiling has a scaling self-similarity, and so can be thought of as a fractal. Penrose originally discovered the P1 tiling in this way, by decomposing a pentagon into 6 smaller pentagons and 5 half diamonds. He then observed that when he repeated this process, the gaps between pentagons could all be filled by stars, diamonds, boats and other pentagons. By iterating this process indefinitely, he obtained one of the 2 P1 tilings with pentagonal symmetry. Robinson triangle decompositions. The substitution method for both P2 and P3 tilings can be described using Robinson triangles of different sizes. The Robinson triangles arising in P2 tilings are called A tiles, while those arising in the P3 tilings are called B tiles. The smaller A tile, denoted AS, is an obtuse Robinson triangle, while the larger A tile, AL, is acute. In contrast, a smaller B tile, denoted BS, is an acute Robinson triangle, while the larger B tile, BL, is obtuse. Concretely, if AS has side lengths, then AL has side lengths. B tiles can be related to such A tiles in 2 ways. If BS has the same size as AL and BL is an enlarged version IAS of AS, with side lengths this decomposes into an AL tile and AS tile joined along a common side of length 1. If instead BL is identified with AS, then BS is a reduced version of AL with side lengths a joining a BS tile and a BL tile along a common side of length 1 then yields an AL tile. In these decompositions, there appears to be an ambiguity. Robinson triangles may be decomposed in two ways, which are mirror images of each other in the axis of symmetry of the triangle. In a Penrose tiling, this choice is fixed by the matching rules furthermore, the matching rules also determine how the smaller triangles in the tiling compose to give larger ones. It follows that the P2 and P3 tilings are mutually locally derivable. A tiling by one set of tiles can be used to generate a tiling by another for example a tiling by kites and darts may be subdivided into A tiles, and these can be composed in a canonical way to form B tiles and hence rhombs. The P2 and P3 tilings are also both mutually locally derivable with the P1 tiling. The decomposition of B tiles into A tiles may be written, BS equals AL, BL equals AL plus AS, assuming the larger size convention for the B tiles, which can be summarized in a substitution matrix equation. Combining this with the decomposition of enlarged IA tiles into B tiles yields the substitution, so that the enlarged tile IAL decomposes into two AL tiles and one AS tiles. The matching rules force a particular substitution. The two AL tiles in AIAL tile must form a kite thus a kite decomposes into two kites and a two half darts, and a dart decomposes into a kite and two half darts. Enlarged IB tiles decompose into B tiles in a similar way. Composition and decomposition can be iterated, so that, for example, the number of kites and darts in the nth iteration of the construction is determined by the nth power of the substitution matrix, where Fn is the nth Fibonacci number. The ratio of numbers of kites to darts in any sufficiently large P2 Penrose tiling pattern therefore approximates to the golden ratio I. A similar result holds for the ratio of the number of thick rhombs to thin rhombs in the P3 Penrose tiling. Deflation for P2 and P3 tilings. Starting with a collection of tiles from a given tiling, deflation proceeds with a sequence of steps called generations. In one generation of deflation, each tile is replaced with two or more new tiles that are scaled-down versions of tiles used in the original tiling. The substitution rules guarantee that the new tiles will be arranged in accordance with the matching rules. Repeated generations of deflation produce a tiling of the original axiom shape with smaller and smaller tiles. This rule for dividing the tiles is a subdivision rule. Consequences and applications. Inflation and deflation yield a method for constructing kite and dart tilings, or rhombus tilings, known as up-down generation. The Penrose tilings, being non-periodic, have no translational symmetry the pattern cannot be shifted to match itself over the entire plane. However, any bounded region, no matter how large, will be repeated an infinite number of times within the tiling. Therefore, a finite patch cannot differentiate between the uncountably many Penrose tilings, nor even determine which position within the tiling is being shown. This shows in particular that the number of distinct Penrose tilings is uncountably infinite. Up-down generation yields one method to parameterize the tilings, but other methods use Amin bars, pentagrids, or cut and project schemes. Related tilings and topics. Decagonal coverings and quasicrystals equals. In 1996, German mathematician Petra Gummelt demonstrated that a covering equivalent to the Penrose tiling can be constructed using a single decagonal tile if two kinds of overlapping regions are allowed. The decagonal tile is decorated with colored patches, and the covering rule allows only those overlaps compatible with the coloring. A suitable decomposition of the decagonal tile into kites and darts transforms such a covering into a Penrose tiling. Similarly, a P3 tiling can be obtained by inscribing a thick rhomb into each decagon. The remaining space is filled by thin rhombs. These coverings have been considered as a realistic model for the growth of quasicrystals. The overlapping decagons are quasi-unit cells analogous to the unit cells from which crystals are constructed, and the matching rules maximize the density of certain atomic clusters. Related tilings equals. The three variants of the Penrose tiling are mutually locally derivable. Selecting some subsets from the vertices of a P1 tiling allows to produce other non-periodic tilings. If the corners of one pentagon in P1 are labeled in succession by 1, 3, 5, 2, 4 and unambiguous tagging in all the pentagons is established, the order being either clockwise or counterclockwise. Points with the same label define a tiling by Robinson triangles, while points with the numbers 3 and 4 on them define the vertices of a Tyrn-Navet tiling. There are also other related unequivalent tilings, such as the hexagon boat star and micolor Euro-Rath tilings. For instance, if the matching rules for the rhombus tiling are reduced to a specific restriction on the angles permitted at each vertex, a binary tiling is obtained. Its underlying symmetry is also fivefold, but it is not a quasicrystal. It can be obtained either by decorating the rhombs of the original tiling with smaller ones, or by applying substitution rules, but not by de Bruij's cut and project method. Penrose Tilings and art equals, the aesthetic value of tilings has long been appreciated, and remains a source of interest in them. Here the visual appearance of Penrose Tilings has attracted attention. The similarity with some decorative patterns used in the Middle East has been noted, and Lew and Steinhardt have presented evidence that a Penrose tiling underlies some examples of medieval Islamic art. Drop City artist Clark Richert used Penrose rhombs in artwork in 1970. Art historian Martin Kemp has observed that Albrecht Darwin Rare sketched similar motifs of a rhombus tiling. San Francisco's new $4.2 billion Transbay Transit Center is planned to have perforations in its exterior's undulating white metal skin in the Penrose pattern. The floor of the atrium of the Molecular and Chemical Sciences building at the University of Western Australia is tiled with Penrose tiles. The Andrew Wiles Building, the location of the Mathematics Department at the University of Oxford as of October 2013, includes a section of Penrose tiling as the paving of its entrance. The pedestrian part of the street Keskuskatu in Helsinki is paved using a form of Penrose tiling. The work was finished in 2014. See also, List of aperiodic sets of tiles, Zell-Leach, Girat tiles, Patterns and Nature, Pinhole tiling, Quark-reversal tiling, Pentagonal tiling. Notes. References. Primary sources Berger, R., The Undecidability of the Domino Problem, Memoirs of the American Mathematical Society 66, de Bruij, and G., Algebraic Theory of Penrose's Non-Periodic Tilings of the Plane, I, 2, Indagations Mathematicae 43, 39 Euro66, doi, 10.1016/1385-7258, 81, 90017-2. Gummelt, Petra, Penrose Tilings as Coverings of Congruent Decagons, Geometrie Dedicata 62, doi, 10.1007/BF00239998. Penrose, Roger, The Role of Aesthetics in Pure and Applied Mathematical Research, Bulletin of the Institute of Mathematics and its Applications 10, 266 ff. US 4,133,152, Penrose, Roger, Set of Tiles for Covering a Surface, published June 24, 1976, issued January 9, 1979. Robinson, R.M., Undecidability and Non-Periodicity for Tilings of the Plane, Inventions Mathematicae 12, 177 Euro190, Bibcode, 1971 in Mat 12-177R, doi, 10.1007/BF01418780. Schechtman, D. Bloch, I. Gracious, D. Kahn, J. W., Metallic Phase with Long-Range Orientational Order and No Translational Symmetry, Physical Review Letters 53, 1951 Euro 1953, Bibcode, 1984 PHRVL 53.1951S, doi, 10.1103/PhysRevLet 53.1951, Wang, H., Proving Theorems by Pattern Recognition 2, Bell Systems Technical Journal 40, 1 Euro 42, doi, 10.1002 per Joule 1538-7305.1961. TBO3975X. Secondary sources equals, Austin, David, Penrose Tiles talk across miles, feature column. Austin, David, Penrose Tilings tied up in ribbons, feature column. Kulig, Carol. Curry, Jarko, on aperiodic sets of Wang tiles, Foundations of Computer Science, Lecture Notes in Computer Science 1337, pages 153-162, doi, 10.1007/BFB00520884, ISBN 3-540-63746-X, Gardner, Martin, Penrose Tiles to Trapdoor Ciphers, Cambridge University Press, ISBN 978-0-88385-521-8, ISBN 978-0-7167-1986-1. Chapter 1 is a reprint of Gardner, Martin, Extraordinary Non-Periodic Tiling that Enriches the Theory of Tiles, Scientific American 236, 110 121. Godrache, C. Lana section on, F, a simple example of a non-Pisot tiling with fivefold symmetry, Journal de Physique I2, 207 220, bibcode, 1992 JPHY1. 2207G, doi, 10.1051/JP1 1992134. Gra 1/4 NBAUM, Branco. Shepard, G.C., Tilings and Patterns, New York, W. H. Freeman, ISBN 0-7167-1193-1. Kemp, Martin, Science in Culture, A Trick of the Tiles, Nature 436, 332, bibcode, 2005 Nature 436 332K, doi, 10.1038/436332A. Lana section on, Fra copyright Dow copyright Rick Billard, Luke, Two-dimensional system with a quasi-crystalline ground state, Journal de Physique 49, 249 256, doi, 10.1051/JPHYS, 0198800490202490. Lord, each. Ranganathan, S., the Gummelt decagon is a quasi-unit cell, actor crystallographic A57, 531 539, doi, 10.1107 per second 01087673010075004, Liu, Peter J. Steinhardt, Paul J., Decagonal and Quasi-Crystalline Tilings in Medieval Islamic Architecture, Science 315, 1106 1110, bibcode, 2007 Sci. 315.1106L, doi, 10.1126/Science 1135491, PMID 17322056. Luck, R., Dar 1/4 Rare Kepler Penrose, The Development of Pentagonal Tilings, Materials Science and Engineering 294, 263 267. Makovicki, E., 800-year-old pentagonal tiling from Maragha, Iran, and the new varieties of aperiodic tiling it inspired, in Ihaljatai, Fivefold Symmetry, Singaporea London, World Scientific, pages 67 86. Penrose, Roger, Pentaplexity, Eureka 39, 16 22, Pentaplexity, a class of non-periodic tilings of the plane, the mathematical intelligence Adu, 32 37, doi, 10.1007/BF03024384. Senchal, Marjorie, Quasicrystals and Geometry, Cambridge University Press, ISBN 978-0-521-57541-6. Steinhardt, Paul J. Jiang, Yuongchai, A Simpler Approach to Penrose Tiling with Implications for Quasicrystal Formation, Nature 382, 431 433, bibcode, 1996 Nature 382 431s, doi, 10.1038/382431 AO. Zaslevskia, G.M. Sagdiyev, Roland Z. Yuzikov, D.A. Chernikov, A.A., Minimal Chaos, Stochastic Web and Structures of Quasicrystal Symmetry, Soviet Physics USPEC 31, 887 Euro 915, Bibcode, 1988 SVPHU 31887Z, doi, 10.1070/PU 1988 VO31N10ABEH005632. External links: Wellstein, Eric W., Penrose Tiles, MathWorld. John Savard. Penrose Tilings Quaderblock.com. Retrieved November 28, 2009. Eric Wang. Penrose Tiling Nintendo.net. Retrieved November 28, 2009. E. Harrison D. Fretler Paragraph H. Penrose Rome. Tilings Encyclopedia. Department of Mathematics, University of Bielefeld. Retrieved November 28, 2009. Kevin Brown. On de Brouage Grids and Tilings Mathpages.com. Retrieved November 28, 2009. David Epstein. Penrose Tiles. The Geometry Junkyard www.exursi.edu/Epstein. Retrieved November 28, 2009. This has a list of additional resources. William Chow. Penrose Tiling Architecture. Retrieved December 28, 2009. Penrose's Tiles Viewer.